Um, it is my pleasure today to introduce David Gallacher, who is a PhD student at McGill University. Yeah, for many years now, he's been working on light detectors for use in noble liquids, from his time at Carleton, working with liquid argon, and now at McGill working with liquid xenon. And so today he's going to tell us about some developments for the light collection system for the next experiment. Take it away, David.
Thanks, Rob. Yeah, thanks. So this looks okay for people. So today I'm gonna
It looks good.
great. Um, yeah, like so Rob mentioned, I'm going to tell you about doing R&D for the Nexo light collection system, but I'm also going to talk a little bit about why we're doing this and kind of motivate the whole reason for doing these very detailed studies of the performance of our detector and the details of how our devices actually work. So yes, the title of my talk is Shedding Light on Neutrino Nature, which is about R&D for the Nexo detection system. So just as a brief overview, there's three main parts of my talk. The first, I'm just gonna say, like I said, I'm gonna introduce some motivation for why we're studying, why we're building this detector, why we need to understand the light detection system so well, and I'll tell you exactly what Nexo is, and some background information for what we're searching for, as well as I'll talk about the Lolex experiment, which is the main R&D prototype detector that I work on at McGill University, and some of the recent updates from measurements we've been doing with that system. And then I'll end with some discussion about how all of this R&D work with Lolex ties into the overall light detection system for Nexo, which, since Nexo is still a proposed experiment, the main impact is improving and the accuracy of our simulations. So I'll talk about how we actually do our simulations for light transport in Nexo. Great. So yeah, neutrinos and neutrinoless double beta decay. So the first thing that you should know is that neutrinos are weird, which is exciting for us, people who study neutrinos and kind of the edges of what is currently known in particle physics, looking for new physics, as we call it. So neutrinos themselves come in three different flavors. So they have they're electron flavored, they're muon flavored, or they're tau flavored. And this corresponds to the three generations of matter in the standard model, and they have equivalent leptons that are related to the same flavor, so the electron, the muon, and the tau. So there's a key observation that was made a while ago now, but is still very important for us, which is that neutrinos oscillate. And the important thing about neutrinos oscillating is that because they oscillate, they're oscillating between flavor states, so that a neutrino that's made in one flavor state is say as an electron neutrino in a some kind of nuclear decay, has some probability to be observed in a different flavor state as it is being transported through space-time. So and the way that it travels, it mixes into these new flavor states is because it is in a superposition of its mass states. And the only way that this can happen is because at least two of the three states must be massive, which is a new observation, because in the standard model of particle physics, which is kind of our reference guide for all the types of interactions that can happen between particles and what particles can do as currently observed, they are massless in the standard model. So that's an important observation. The fact that they oscillate means that at least two of the states are massive. There's still, it's unlikely that the lowest mass state is zero, but it could be close to zero. And because at least two of the states are massless and they're massive, and because they're massless in the standard model, this is an exciting avenue to look for new things, because the standard model is pretty tight. There's not a lot of places where it's giving, and people have been trying for a long time now to find physics beyond the standard model, and without much luck. So there's some open questions in neutrino physics that are really important to understand, that we're really working on, which is you know, are there just three flavors? So there's possibilities or options for there to be more flavors, but we call these three active flavors because they participate in the standard model interactions. But it could be that there's other flavors or types of neutrinos that exist that don't interact the same way as their more standard model like particle counterparts. We don't know what the masses are of the neutrinos, so this is really important. We don't know why they have mass, and we don't know what the masses are. So a good way to kind of try to understand the neutrino at the first start is just to really measure the mass and to understand how it's getting the mass and how much mass it has. And that'll hopefully open up avenues for us to understand on a more fundamental level exactly how they get their mass, because they don't get it the same way as all the other standard model particles. And in particular, we also don't know which way these states are ordered. It could be that the states are ordered in one direction, or it could be that what we think is the heaviest state is actually the lightest state. And that'll explain that in the next slide. And then we also don't even know what the nature of the particles are. It's possible that they're a new type of fermion that we've never observed before. So there's a lot of ways you can measure the neutrino mass scales. So I say mass scales importantly because not all of these are actually measuring the neutrino mass, and it's a little complicated. So there's indirect ways to measure the mass scales. You can measure it indirectly, which is the way that we have done historically so far, which is through the neutrino oscillation experiments. And the parameter that the oscillation experiments are sensitive to, what they get in their measurements, is what we call the mass squared splittings, which is the difference in the squared mass states between two of these states. So we can measure the difference in the mass, or the squared differences in the mass, and then take the square root of that, and we get something that is proportional to the mass difference between those two states. But it doesn't tell us what the actual mass scale is. It just kind of gives a hint. If this is a really small number, it could be that these are two very massive things that are only differ by a small amount, or it could be that they're two small things that differ by a reasonable amount. We're not sure. There are other ways to measure the neutrino mass indirectly. The neutrino mass is an important parameter in cosmological models that try to explain the evolution of the universe. So they include the neutrinos and neutrino mass in there as a free parameter, and they can extract this from the fits to structure formation. And this actually is what is sensitive to is the sum of the mass states. So the sum of all neutrino masses is what comes out of those models, because they all kind of interact kinematically in these cosmological simulations. So it's first order only. And then we can measure the mass scales directly. The really great way and the best way to do this, I think, is through just directly measuring the mass of the neutrino. Unfortunately, it's just really, really hard because the mass limits from cosmological models give us a hint. And there has been measurements already looking for the neutrino mass by looking at the beta decay spectrums that set the neutrino mass to be about 1 eV or less. And this is a very small number. This is, many decades smaller than the electron mass, which is already the lightest particle in the standard model. So we're talking about truly small numbers, and it's hard to measure neutrinos because they're neutral particles and they don't interact with most things. So the way that we're approaching this is by looking for something called neutrinoless double beta decay, which measures something slightly different from what you get in the mass measurements, but is still a direct probe for the overall mass scales of the neutrinos. What is neutrinoless double beta decay? It's a long word. Well, first we have beta decay, which is a type of nuclear decay that can occur and is occurring all the time. It's occurring in your bodies right now, quite a lot of it actually. There is many different half-lives of beta decay isotopes, depending on what they are. They go all the way up to something, like the age of the universe. Double beta decay is a very rare process. And this is when you have, rather than having one nucleon decay, you have two nucleons simultaneously decay, and the half-life of this, isotopes that have been measured to do this, is incredibly long. So this is 10 to the 18 to 10 to the 21 years. This is 10 to the 10 years longer than the age of the universe, which is it's as long as the age of the universe has been to us, since we started this talk. It's an incredibly large difference between regular beta decay and double beta decay. So you need a lot of material to measure something so weak. Now, neutrinoless double beta decay is a hypothetical proposed form of beta decay, where rather than having just a double beta decay, very rarely, and the half-life limits here are 6 orders of magnitude larger than the ones from the double beta decay, the measured values. So very rarely 1 in a million or 1 in 10 million or maybe 1 in a billion of the double beta decay events could be a neutrinoless double beta decay event, where we have no neutrinos coming out or no antineutrinos coming out and just electrons. Now this is an important thing. This is why do we want to search for a neutrinoless double beta decay? Well, searches for neutrinoless double beta decay are direct probes of lepton number violation and physics beyond the standard model. And that's a kind of a loaded term, lepton number violation, but what it means is, I can illustrate from these diagrams here, these Feynman diagrams, where on the left side you have a regular double beta decay, where you have some standard model particles at the beginning, and you get out all of your particles at the end, and if you add up all of the matter terms here and all the antimatter terms and matter terms here, they cancel each other out, and you get something that is 0. So all the matter and antimatter, some of it can change from one to the other. I mean, you can make matter as long as you also make antimatter, and that cancels itself out, which is what is happening here with these electrons and anti-electron neutrinos. So in this case, lepton number is conserved. But for neutrinoless double beta decay, if this is to occur, and if we do see this observation, this is a process where matter and antimatter are not conserved, and we actually have matter generation on the right side without any antineutrinos to balance out the equation. So the lepton number is not just violated here, it's maximally violated. And this is really important because it has really interesting and far flung implications for things in cosmological evolution, like the baryon asymmetry problem, which is just posing the question of why is there stuff in the universe at all? Because in all of the processes we've observed in the standard model, basically all of the processes produce the same amount of matter as antimatter. So how is it that we live in a matter universe and there's not really any antimatter going around? At some point, the scales had to have tipped. So that's what we're trying to understand, is exactly how can we tip those scales? And it's possible that lepton number violation being violated so maximally in neutrinoless double beta decay interactions through the neutrino portal is a way to explain this really long-standing problem. And this is also interesting just in terms for fundamental symmetries and fundamental particle physics in general, because if we do observe neutrinoless double beta decay, this is not just a new form of generating matter, which we'll have to figure out exactly how the neutrinos are getting this mass, but it is a positive confirmation that neutrinos are a new form of matter, which we call Majorana fermions. And Majorana fermions are different. Most of the particles that you're familiar with, if you're familiar with fermions in general, they're spin 1/2 particles, and fermions come in particle or antiparticle states. So you can have an electron, or you can have a positron, you can have a proton, or you can have an antiproton, and those are all fermion states, and they're all Dirac fermions. They obey something that we call Dirac statistics, and I'm not going to get into the details of that, partially because I don't really know them as well as I do the detectors, but so Dirac fermions come in either particle or antiparticle states. But like I said, if we observe neutrinoless double beta decay, it's a positive confirmation that neutrinos are something called Majorana particles, and Majorana fermions are their own antiparticles. So there's only one state, and it's a combination. So this is possible because if neutrinos are Majorana fermions, they can interact with themselves, and we can draw Feynman diagrams like this one where we get just electrons out and no antineutrinos. So, Majorana fermions would be very exciting, and this is really enabled by the fact that neutrinos, unlike many other particles in the standard model, are neutral particles, and they're fundamental neutral particles, unlike the neutron, which is composed of quarks. Neutrinos are fundamental particles, and they have no charge, and which means that if we change their quantum numbers from particle to antiparticle, everything stays conserved. There's some things, details beyond the tree level, but to first order things, you can swap all the quantum numbers and you get the same thing for neutrinos. So this is an enabling feature. If we observe neutrinoless double beta decay, neutrinos must be at least have some kind of Majorana component. And if we do observe Majorana fermions, then it would be very exciting. So for neutrinoless double beta decay, neutrinoless double beta decay is only really observable in an isotope that already is capable of doing double beta decay. And like I said, double beta decay was a very rare process, 10 to the power of 10 longer than the age of the universe, which means that if you want to observe a statistically significant amount of decays from that mode, you need a ton of stuff, like literally tons of material. And you can only get double beta decay in a very small number of isotopes, about 30 of them, is what we know of that can do this decay. And that's because in order for you to do this very rare decay, double beta decay, you have to be forbidden from performing just a single beta decay. And this is only true for a certain set of isotopes based on their nuclear configurations. And the one that we're focusing on is an isotope called xenon-136. And xenon-136 is a nice isotope for this. It has a high Q value, which means that it's above a lot of the natural radioactive backgrounds that would interfere with our measurements, and there's quite a lot of it. So the natural abundance is about 9%, which means that you can get a lot of the xenon-136 just by collecting xenon in general. So because the rest mass of cesium-136, which is a single Z translation from xenon-136, is forbidden energetically. You can't go up, or you can't spontaneously create energy. And this allows us to do a double beta decay to barium-136 here. And if we're lucky, and if neutrinos are Majorana particles, then we may also observe the neutrinoless double beta decay version of this. And there are a number of other isotopes that people are looking at, and there are some of our people who are studying neutrinoless double beta decay are using different isotopes, and this is really important because there's a lot of details in the nuclear physics here that kind of you can compare between different isotopes and get a better idea of exactly what's happening inside if we do observe neutrinoless double beta decay. So it's really important to do many different isotopes as you can, yeah, so what does it look like when we see this neutrinoless double beta decay? What are we actually looking for? The experimental signature of neutrinoless double beta decay is a double beta decay event where 100% of the energy available, 100% of what we call the Q value, which is the amount of energy is stored in that is being translated, 100% of that energy goes to these betas that are coming out, those two betas. So this is because conservation of energy is a conservation law that we have to observe. And another feature of these decays is that the betas that come out have to be coming out back to back, and that's because there's only two particles in the decay, which means they have to carry away all the momentum of the parent, which was a nucleus at rest in its own frame of reference. The nucleus was just hanging out there, sitting in our detector. And so that means that if the betas come out after, they have to cancel the angular momentum, which means we get this very clear kind of back-to-back shot of betas coming out. And there are certain detector technologies that try to take advantage of that feature, although it's not something that we are considering. The other thing that happens is that because you are doing this double beta decay, when you have a neutrinoless double beta decay, you get a 136 barium doubly ionized daughter ion. And what this looks like in terms of the energy that we expect to observe, or what we're looking for inside of our detector, is that we know that we're going to have, if we do see neutrinoless double beta decay, we're going to have 100% of the energy. And that's our main experimental criteria. So in a beta decay spectrum, which you can see on the right-hand side here, you see this distribution, and this is just something like intensity versus something like energy in relative units. So if you have this beta spectrum here, what we'd expect for a certain half-life of neutrinoless double beta decay, you'd expect to have a little spike or a peak right at the end, where The width of this peak is determined by how good your system is at measuring energy, and the height of the peak is determined by the half-life of the decay mode, which is something that we don't know, but we hope is a big number so we can see lots of them, so we get a nice tall peak. If this is a kind of an exaggerated example, this is really unlikely for something like our detector, but something more like this, where it's a million times smaller, is more typical, where you have the endpoint somewhere around here, and the decay is just barely peeking out over top. So it's really important to make sure that you have a really good system to measure energy. So if you wanted to go out and build one of these neutral instable beta decay detectors, here's my shopping list that I'm going to give you. You want to have excellent detector energy resolution. You want to have low background capabilities, and that's really essential because we're looking for something incredibly rare. If you have a background of decays or radiation from your environment, it's going to swamp that signal and you'll never see anything. You want to also have a high abundance for the double beta decay mode. And ideally, you also have, and that's just because you won't want things to cost too much. And ideally, you also have unique signal identification capabilities that allow you to pick out these signal-like events that you're looking for, like these double beta decays, from background-like events, which are everything else. And if you can combine all this, you can get a liquid xenon time projection chamber, which is the detector technology of choice for Nexo. And a liquid xenon time projection chamber is, simply an energy integrator. So it measures energy of radiation. It does this with the liquid xenon because liquid xenon is a material that produces both scintillation and ionization. So scintillation photons and ionization electrons, which are proportional to the amount of energy that is deposited into the material from radiation. So we have some kind of nuclear decay that occurs in the center here, produces a bunch of light, produces a bunch of electrons, and we put an electric field and we drift the electrons up and they get read out on a segmented anode that allows us to kind of pixelize where the electrons hit. And we also collect all the light on photosensors around the surrounding surface of the detector on the barrel that integrate all of this scintillation light. And you get XY coordinates from the position of the blob, but when you get to the top, when it's projected onto the top tiles, and you get the Z coordinate from the difference in time from when you see this very fast scintillation signal and when the electrons finally make their way up there, because they have to drift at some finite speed, and you can use that to tell exactly XYZ where your event occurred. So these large-scale monolithic detectors have a lot of beneficial features. They can be scaled very high. They can be made very pure, so it's just xenon in there. It's all made of xenon. We have xenon gas. We turn it into liquid, and we have a complete control. It's atomically pure, or that's what we hope for. We can shield ourselves from external radiation because it's so large and everything is just xenon, and then there's some stuff on the outside to measure the interactions. We're really powerfully discriminating against external gammas. This is because the attenuation length of a gamma is a few centimeters, so the bigger you make your detector, which you can see illustrated on the side here, and we're a 5-ton detector, the bigger you make your detector, the smaller chance these external radiation gammas can actually make it to where you care to measure your signal, which is somewhere in the middle, or your signal is uniformly distributed. You can do 3D position reconstruction, like I said, and there's all sorts of possibilities to do more interesting things, and we're going to take advantage of as much of that as we can. So Nexo is a proposed experiment, so it doesn't exist. It's proposed to search for neutral instable beta decay, and the inner detector itself, which is the thing I'm going to be focusing on, is a single phase TPC, like we saw. And single phase meaning it's just liquid. There are some technologies that use liquid and gas. And we have 5 tons of liquid xenon that's enriched to 90% with xenon-136. And we have to combine both the charge and the light collection signals, and be lucky for us, these signals are correlated. So if you have more light, you have less charge. If you have less charge, you have more light. It's a well-known relationship between those two things. So when we combine all of our signals together, we get really excellent resolution on how much energy was actually available or was produced in that radiation event, or in this decay. So we've designed our detectors, so we try to make it as background free as possible. We try to make it as sensitive as possible, and we put as much stuff in the detector as we can fit. And this allows us to reach a target sensitivity of longer than 10 to the 28 years, looking for neutral double beta decay, which means that if it has a half-life less than 10 to the 28 years, give or take, we should see it inside Nexo. which is really exciting because it's never been observed before. And we hope to build this experiment at the Snow Lab cryo pit. So because this is a light detection talk, I'm going to tell you a little bit about the light detection system for Nexo. So Nexo uses technology called silicon photomultipliers, which are single photon sensitive light detectors. We have individual SIPMs on tiles, and then tiles that make up big modules, and we put all of those tiles on a big thing that we call a stave, and then the whole barrel is instrumented with silicon photomultipliers by scaling up, from one stage to the other. We have SIPMs on tiles, tiles on staves, and we have 24 of these staves that surround the inside, which means that we're looking in with all of these light sensors to better understand and be able to really pixelize and detect, maybe even image, where the events are from just from the light system to complement what we see from the charge system. Now, this is quite a lot of photo coverage. So this is 4.6 meters squared and 8,000 channels, which is about 50,000 of these silicon photomultipliers, which are summed together. And this is one of the biggest experiments or proposed experiments to use silicon photomultipliers. It's a massive area to cover with these very, very sensitive devices. So we really want to understand that the device performance as well as we can. So this is slightly different from how I normally talk about this, but I wanted to kind of explain what it means for us to actually be sensitive to neutronless double beta decay or be a discovery experiment. I find people often just show limit plots, and I remember being very confused the first time I saw a limit plot. So what exactly does it mean if we have a limit on neutronless double beta decay, or what does it mean to be sensitive to it? So we are a pseudo background free experiment, which means that pseudo as in because we can't get rid of all backgrounds, but we can be insensitive to many of them through our discrimination techniques and analysis. This means that we're sensitive to single individual events of double beta decays near the Q value. And now there's two scenarios that could occur. We could see a signal that looks like it is neutronless double beta decay. It's in the right place, it's got the right energy, it's got the right characteristics. It doesn't have any of the background-like features that we can discriminate against. And it's not explained by the amount of backgrounds that we should see. And backgrounds are just radiation from all other sources. So it's really challenging to look for rare events that have never been observed before, because you have to measure everything and then throw it all away. So you have to measure everything, know what it all is, and then get rid of it all and look for the thing that you hope to be remaining. Now, if we can't explain what we see by the background model, this is what we call discovery potential. We actually have the opposite. This is, it could be that we're seeing neutronless double beta decay. And if we only see background, or we see something that's consistent with our background model, we set an upper limit, and this upper limit is at a 90% confidence level. And that just comes from the fact that we were sensitive to a certain number of events in a certain amount of time, which is the rate. You can say a rate is like, is given by this relationship with some kind of time constant, and the time constant you can represent as a half-life for this decay mode. So what we say is that, as we integrate in time, as we have more and more potential for decays and more time we're integrating, we're more and more sensitive to longer half-lives. And after 10 years, we'll be sensitive to 10 to the 28. Great. So moving on to the experimental side of things. So I work with the Lolix experiment, which is a liquid xenon R&D experiment at McGill. It's a small scale modular experiment. We've had two main experimental phases to date. We have the first phase, which I'm going to talk about in a good amount of detail, and then the second phase, which I'll talk about and I'll just kind of go over briefly. And so in phase one, we had a detector that looked like this on the side here. It was a 96 SIPMs in an octagonal prism geometry, and we had this strontium-90 source, which is a beta decay source that produced scintillation photons in the middle here. And we're really trying to understand how the SIPMs respond and how the light is transported throughout our detector. We need to be able to constrain this. So for this phase of the experiment, we had our SIPMs, packaged in groups of 4, and we actually covered 23 out of 24 of the packages with filters to optically separate scintillation light from non-scintillation light. And we had one package of 4 that was not filtered, and one package that was that had just a scintillation filter. So what these filters do is allow us to separate our liquid xenon scintillation from something called SIPM external crosstalk, which is the thing that we're trying to measure. And you can see what this looks like here. In our green curve, we have the the filter cutoff or the scintillation excluding filters. We go the long pass ones. So like I said before, liquid xenon is a scintillating material. It produces vacuum ultraviolet light. So this is 175 nanometer light. It's very, very high energy photons. They can't travel through air. They get absorbed. That's why we call it vacuum ultraviolet. You need to be in a vacuum to see it. Single silicon photomultipliers, like I mentioned, are single photon sensitive solid state sensors. And we use the SIPMs to count photons from the radiation in liquid xenon that gives us a proportional measure of the energy of the event. And this is fundamentally how these detectors work. Unfortunately, you can't get your signal for free. Whenever you have a signal, you're going to have noise or fluctuations or random variations in your signal that we can hopefully constrain so we can understand our signal better. And for SIPMs, this noise comes through primarily from the fact that the photons themselves are detected through what we call an avalanche process, where the photons come in and create an avalanche in this semiconductor PN diode. And this avalanche is the source of much of this correlated noise that comes from the signal. So we have a lot of different things that can happen. You can have direct kind of small scale after pulsing. You can have photons come out and transport to other pixels in your array of your sensor. They can leave and get absorbed and then randomly walk back in later, or they can just leave entirely. And this noise can be internal, external, and the noise that I'm focusing on today, which is hasn't been constrained very well so far, is called external crosstalk, where you have a photon producing the avalanche that just leaves and goes to the other side of your detector. So during this detection process, these photons are produced, and the near infrared photons these photons are near infrared, and that's been confirmed from separate measurements. And they may escape and be detected elsewhere, and we would call this external crosstalk, or SIPM external crosstalk, or EXCT. And this is a source of correlated avalanches that we need to constrain. So we want to characterize the external crosstalk inside of our liquid xenon detector because it matters to do it in the same kind of configuration. And we want to create a simulation model, which is really important for a proposed experiment. We need to simulate and have a good understanding of how our detector like Nexo is going to perform, and that means including effects like external crosstalk in that simulation. And we want to be able to predict the impact of this fluctuation or this noise contribution overall. So what does this look like inside LOLEX? Well, first you have the scintillation event. It produces a bunch of photons. The photons come over, they get detected, produce more photons. One makes it out, and then maybe we see it on the wall over here. And so this is the signal channel that we're looking for. We're looking for photons that are produced in our unfiltered or kind of bare channel that has no blocking filter. And we're looking to detect these near infrared photons in these SIPMs that have filters over them, so we have less background because they're already filtering out a lot of the scintillation light. So what's the impact of this? Why do we really want to understand this effect? The impact is that we're using 50,000 SIPMs in Nexo, so we need to understand exactly all the sources of correlated noise for that, and because we have this cylindrical geometry where all of the SIPMs face each other, this effect is enhanced. The light comes from here, it can bounce around and then maybe get detected. And it's got a lot of opportunities to be absorbed by a photosensor rather than just going off into space. So we really need to evaluate the impact of SIPM external crosstalk on the main thing that we care about, like energy resolution. But if you're a dark matter detector like Argo or DarkSide, you care probably about the threshold of your detection and your position reconstruction and all the other things, as well as energy resolution, where this can smear out those measurements. And what does that look like in terms of the actual measurement? Is that we want to have 1% energy resolution for Nexo. This is our requirement to get the sensitivity that we are aiming for. And we have two different detector systems that are combined. Like I said, in order to reach our resolution targets, we need to understand how our signal fluctuates. So resolution is a measure of how much fluctuation you have in your measurement. I measure 1 MeV, but tomorrow it's 1.01, and yesterday was 0.99. And how much that fluctuates depends on random variations in your detector response, as well as effects of correlated noise. So what we expect is that this is what our light contribution is to the overall detector resolution, is these dashed lines. And if you add external crosstalk to this, which this is a plot from a paper from a couple of years ago that we published on our system, But if you add external crosstalk to this, it's possible that this, curve continues to go up or it goes up faster. And what we really want to do is we want to understand what exactly is this effect on these curves. So that's the big picture target. So like I said, when we see this external crosstalk in LOLEX, what we're looking for in terms of our measurement is the timing. So the signature of external crosstalk inside LOLEX is two pulses that are coincident in time from different sensors across the detector. Like I showed you in that animation, we have detected photons there that produce an avalanche. We see that pulse in our electronics, and then because of that avalanche, more light was produced, and some of that light may have escaped and hit another sensor and created an avalanche at basically the same time. And for us, this is more or less exactly coincident because the transportation time, the amount of time it takes for these photons to fly through the detector is like 100 to 1,000 times shorter than our timing capabilities for actually measuring. So incredibly fast picoseconds to travel across the detector, or sub-picoseconds. So what we expect to see is something like this, where we have an unfiltered channel signal, and then sometime around the exact, really close to that, we expect to see something else. And what we do is we look late in our event window, so far after this initial scintillation burst from the xenon radiation, and or the radiation in xenon, and we look for correlations between these delayed pulses. So this is kind of a low light level correlation. And inside our actual detector, this is what the distribution of those pulses looks like. So this is the average pulse rate for all channels together. And we can see up at the start, we're seeing tens of pulses on average for every single event. And where we're looking is a much quieter or dimmer region of the detector, which we call our low occupancy window, which is just kind of far after the main event happens. And this is kind of where we're looking for these coincident events. Now, if you collect many pairs of these pulses and you measure the time difference between them, this is a measure of how coincident they are. Like I said, the time difference between pulses that occur at the same time is 0. So if we have external crosstalk, what we expect to see is exactly what we see on the right from our data, which is a kind of an uncorrelated random fluctuations. We call this a combinatorial background, just from the fact that there happen to be pulses nearby each other. They have this feature, this flat background. And then for our signal, what we expect is a peak right at 0, where we expect to see these external crosstalk photons are actually seeding and creating avalanches in other sensors. And then you can measure the correlation strength of this just by taking the amount of signal that you have in here and subtracting what you expect for the background, and you normalize to how many pulses could have made this light. Now, this is what we measure in our detector, and there's an important thing that made this measurement really hard, actually, is the fact that some of the light is coming from our unfiltered channels and going to the filtered ones, and some of the light is actually coming from a filtered channel, because that's the one that saw the photon first, and then getting detected on the unfiltered channel. And the acceptance for these two directions is wildly different, because we have one unfiltered package and 22 of these long pass packages. So we actually really needed to simulate this effect to better understand and be able to tease out the contribution from external crosstalk, and not just have the fact that we have many channels and bad acceptance for what we're looking for. So we did these simulations, and we developed a whole simulation model to be able to do this in JON 4. And the way this works is kind of illustrated on the right here, is that after we detect a photon at some position like 1, we model the emission of light from the avalanche as an isotropic distribution. In reality, we actually kill the ones that go back down, because they just double count. But the ones that go in the upward hemisphere can actually have a chance to escape, and that escape probability is coming from the optics of these interfaces, so the refractive index and the coupling between these 3 materials. And there's really high refractive index in silicon, and fairly reasonable refractive indices in liquid xenon and silicon dioxide. So what ends up happening is you get quite a lot of refraction out. And if you take a look at the distribution of all of the photons that we expect to come out as a function of angle from the surface of the SIPMs, you get this very broad distribution, where the theta is the y-axis here, and this is wavelength here. So you get a very broad distribution that's centered around 45 degrees because of the strength of this refraction. And we do this model directly in JON 4, and this is the output map of what it looks like once these photons get escape the device. So by interpolating our model of external crosstalk, which is informed by these simulations that we did and the data that we measured, we can estimate the amount of light that has to escape each avalanche on average. So our assumption beforehand when we started this study is that sometimes avalanches produce light. But now our understanding is that every time avalanches produce light, and sometimes that light escapes. And it's just that because the optical coupling from within silicon to liquid xenon is quite poor, that you don't get that much light out. But in different setups and different scenarios with different detectors and different SIPMs, you may actually have much more light come out if the optics is better. So what we do is we wrote down this model that estimated this contribution from that we were trying to measure in data, this p-core correlation probability, as a function of all of the things that we could think of for that could contribute to that effect. And a big thing is that we're looking for this amount of light on average per avalanche to come out. And a bunch of other parameters, which some of them come from simulations like these p forward, p backwards, which are the average combined transport and detection efficiency for the photons that we saw that distribution for. And some of them we just have to measure in data to get some rate scaling so that we know what we're looking for. And this last one here is just known because we've measured it in the past. And then what we're looking for is just the observable. So what we do is we interpolate our model, and we interpolate our model values, which are these pink and yellow curves, with the data that we measure and take into account all of our uncertainties. And the points where these two lines cross is the best fit value for the number of photons emitted from xenon that can describe our data. So what we see is something like 0.5 photons at 4 volts and a little bit more, 0.6 photons at 5 volts. We were taking data with 2 different overvoltages on the SIPMs, and a lot of this work was actually written up in an archive or a preprint that is now available on the archive there. So if you'd like to learn more about how exactly all this details work and where these things come from, but there's kind of 2 important things that I wanted to mention is that we measured the direct external crosstalk probability, so the probability from one avalanche to the other, and we see it's a few percent. We measured the ratio of these 2 parameters versus the gain, which is the ratio of the applied voltages, and they're basically perfectly consistent. So the increase from 4 volts to 5 volts is expected to be a gain increase of 1.25, and the amount of light that we see is 1.25 times more, which is a good cross check for that we're understanding the detector response well. And we really want to extract this detector agnostic parameter NXE because, like I was showing you before, all these simulations were really necessary to understand the effect of external crosstalk. And that's because it's so geometric, because the light has this non-uniform distribution. It bounces around the detector. It depends on where all your sensors are oriented with respect to each other. So it's very detector specific. So we wanted to be able to pull out a number that other experiments and other detectors could use to inform their own models rather than just publishing what we observe to be the probability. So this is a lot of the work went into building the simulation model and understanding it well enough so that we could actually do this extraction. And we have a lot of systematics. You can see our error bars are quite large because we have to really understand our optical properties, and we're just missing data for many of them. So that's a big source of our optical properties, is that we have data at room temperature but not cryogenic. We have data at cryogenic but not the right wavelength, and we have to kind of piece together everything to make it work. Okay. So the phase 2 of our detector, which I mentioned before, is what's happening next. So we've already ran our first phase of the experiment. We took data and we had some issues with cooling with our old detector, and you can see how inefficient it was over here. We were cooling with liquid nitrogen before, and we had so much liquid nitrogen that was coming out at the end of the system. We started to freeze everything, and then we put in this heat exchanger, which was a coil of copper in a bucket of water, which very quickly turned to ice. And so it was really challenging. So a lot of the work that I did in the start of my PhD was just replacing a lot of the cooling system and redesigning it to use a cryocooler with a temperature control unit to make sure that we could actually do longer runs and have more stable conditions for actually taking better data. This is a cross section of what it looks like here. You have Lolex, the detector sits in a bath of xenon, and we cool it directly with the cryo cooler on the right hand side. So the detector was also upgraded significantly for phase 2, and we have a nice shot on the right hand side here from the recent installation work, where we also installed a purity monitored electron drift chamber alongside of our new cubic version of the detector, which includes not just Hamamatsu SIPMs, but also FBK SIPMs and a PMT for reference calibrations. And I'm not going to talk about any of the data that we've collected here, but I will show that we recently did a run in January, and it was really great stability wise for understanding, making sure that we're taking good data, and this is going to set us up for success for future data runs. And you can see basically after we do our initial fill, our data taking is rock solid, and until we start to actually recover the thing, other than some small fluctuations due to the fact that they turn off the heat in the building at night, things are very, very stable. So this is really important. We want to understand the stability of the SIPMs in liquid xenon. We want to be able to operate Nexo's system for 10 years continuously, which means that we need to make sure these devices will work for 10 years, or at least for as long as we can, and that we have a statistically significant amount of SIPMs that we're testing in experimental conditions inside a liquid xenon detector, so that we can understand this. And we have a lot of plans for how we're going to do it. And now we're, now we've done a bunch of these test runs with the cryostat, a lot of our work is kind of coming to fruition, and we're going to take a much longer run, hopefully in a few months. Yeah. So kind of transitioning to the end of my talk, and I'll go quickly through my last few slides here about light simulations for Nexo. So for Nexo, we do light simulations, and we use a software called Chroma. Chroma is a GPU-based photon transport simulation. It uses triangular meshes rather than solids like Geon. The Python itself the development itself is in Python, which is quite convenient especially for our newer collaborators. But the core simulation code runs in Q2C, and it does just photon transport simulation. So it does optical photon transport, and it can do some wavelength shifting and other small features, but and then it detects the photons. So we use Chroma's framework, which is open source from the Benlan framework, but it's recently been kind of converged with this new branch from the Pan Neutrino group. And this works in Singularity containers, which is really convenient for us because we can run it on our GPU workstation, but I can also run it on Compute Canada GPU clusters to do really high statistics runs. And this is and one of the really convenient features of Chroma is that the geometry is defined by STL, so you don't have to make a lot of simplifying assumptions. You can design your detector in CAD and then export the STLs, and it's up to 200 times faster for photon tracking than Geon 4, which is notoriously slow. So Nexo uses standalone GPU simulations, as well as we've started using some more integrated simulations. But the main thing that we do is we take our estimated energy response from the Geon transport, and we convert it into scintillation photons that we have to look up the light collection efficiency and detection efficiency from something that is called a light map. So we use Chroma to build a light map that informs our full-scale detector simulation. So a light map is just a distribution of the transport efficiency of the photons from any location inside the detector. And because we have a symmetric detector, we can reduce the dimensionality slightly. So you produced a certain number of scintillation photons from this model called NEST, which is the Noble Element Scintillation Toolkit, which is standard for liquid xenon detectors. And then we use all of the features of the optical transport inside the detector to make this high statistics 10 to the 12 photon map. And then you have to, afterwards, you include all the effects of efficiency and correlated noise and other sorts of fluctuations. So this is what we've been doing so far. And I've been working on upgrading this system. So we've put a lot of upgrades here to expand out to this full wavelength range that we need to be able to simulate external crosstalk for Nexo. And so, if you're familiar with simulations, you know that if you put garbage in, you get garbage out. So a lot of this work was actually just collecting data sets and integrating it directly into the simulation so that we could simulate this full wavelength spectrum of light from the external crosstalk. And this is an example of what that looks like when you run external crosstalks from a given SIPM. You have this very kind of opening, large-scale structure in the distribution of the detected photons. The thing we want to estimate, the thing we really want to understand, to first order at this point, is just how many expected additional avalanche, additional hits, this fluctuation, how much more will we fluctuate up or down from an avalanche on a SIPM anywhere. So we use the normalized distributions, which we take from the Lolex analysis, and which is something like 0.13 photons per avalanche per volt of overvoltage, assuming that it scales linearly. And you combine all of your various effects. So this is the relationship that tells you the number of external crosstalk, hits that you get in excess. So it's something that is proportional to the transport efficiency. The PDE of the detector is the fill factor, which is the amount of surface area that you have, and then what I call luminosity, which is just the distribution of light that is being produced scaled to the actual yield from our measurements from Lolex. And if you want, this is an example of what the PTE looks like here. It does vary quite a bit over wavelength, so you have to include the full wavelength distribution. You can't just assume it's the same. This is a very preliminary result, but what we see is very similar to Lolex, where we have a few percent effect, and as you increase the expectation from higher overvoltages, you get up to maybe upwards towards 10%, sorry. And you should expect similar results for other cylindrical detectors. So Nexo has the higher photo coverage than Lolex by about 10 or 15%. So we're going to see a bit more. But this is just proportional to the amount of SIPMs that you have and how well they are in integrating light. So this is really exciting stuff. So just to conclude here, so we still have some time for questions. Neutrinos are really strange and interesting. And like in science, outliers are usually our friends, not always, but most of the time, if there's weird things happening, you don't understand something, and if you don't understand something, then you have something to learn. And the search for neutrinos double beta decay is a really exciting and promising avenue to better understand fundamental physics, I think, and Nexo is a really well-equipped experiment that is ready to do this and potentially discover this rare form of nuclear decay that has a very significant Canadian contribution and leadership. And we really, one of the things that I work on is just really getting into the nitty-gritty details of how the detector will perform so that we can understand the contributions from all these confounding effects. And this is so essential for precision physics, where you're looking for things that maybe have never been observed before, or you really want to measure something with the smallest error bars possible. You have to consider everything, which is really challenging, but also really rewarding. And with Lolex, we've been providing key input already for the Nexo simulations, and we're going to be doing more studies in the future with an upgraded detector. And the next thing I'm going to work on is getting those last measurements and doing a full Monte Carlo estimate for the Nexo detector response, which includes all of the effects of SIPM external crosstalk, and not just first order, but all orders. So yeah, thank you, and let me know if you have any questions.
Well, thank you, David. That was very interesting. Yeah, really, really great how it kind of all came together at the end. You were able to do the first order correlated avalanches from the external crosstalk in the full Nexo barrel. Really neat. All right, we do have time for some questions. So if you have a question, please indicate in Zoom. All right, I have a couple, so I guess I can start us out.
Yep, sure, Grub.
So showing where I think it was like slide 30 something or something, where you were showing the the index of refractions, how the photons come back out of the silicon through the oxide layer.
Yeah.
Does the thickness of the oxide layer, yeah, exactly this. Does the thickness of the oxide layer matter at all?
Yes, it's a big effect. So, like I said, most of the photons actually don't make it out. And it's not just most, it's the 97% of the photons don't make it out, is what our expectation is based on this kind of isotropic model of emission that we're working with. And a lot of this data that we're looking at is actually informed by measurements from Triumph, where they use a microscope directly over a SIPM to measure the light coming out during the avalanche. So this is the wavelength distribution, and some of the really nitty-gritty optical details are informed by those measurements that are happening in a vacuum setup in a lab at Triumph. And we have the really hard challenge of kind of turning that data in vacuum into data in liquid xenon, which requires you to understand things like the oxide thickness is a big thing. So the amount of internal reflection, total internal reflection you're going to get is really dependent on the oxide thickness. So for example, the Hamamatsu devices, which is part of this study here, is all with the Hamamatsu devices in the first phase of Lolex, have quite a thin oxide layer, which is about 15 nanometers. But the FBKs, which is the other devices that we're starting to work with, and another candidate detector for Nexo, have like 150 nanometer or 100 or so nanometer oxide layer, which is close to the wavelength of the light that we're looking at. So you actually get interference patterns, which make things more complicated. So the oxide thickness does play a big role. So it determines how much interference and reflection you're going to get at the surface. It also determines how much internal reflection you'll get when the light is trying to escape. And I have thought for a while that, if the people who are making systems, obviously external crosstalk is not a feature, it's a bug. You don't want your light detectors to make light. So I've thought for a while now that if they engineered a surface structure that with specific thicknesses, they could probably suppress the external crosstalk even more, just by fine tuning how the optics at this interface, right? By making it almost impossible for the light to be transported out by having some enhanced reflectivity probability from surface structure or specific thicknesses in the layer there. And if anybody works for a SIPM company, you should think about that.
But you'd have to have it destructively interfere over such a range that, like this one here, and on plot on the right, where you've got a 100 nanometer range where you're
It's a broad distribution, because this is
it's hard because it's broad.
We're still not quite sure what the actual physical source of this light is. There's probably a contribution from many different factors like lattice effects, maybe a bit of fluorescence. There could also be what we call Bremsstrahlung radiation from the fact that these electrons are being accelerated very quickly through the lattice. You get kind of this lattice-induced Bremsstrahlung. Yeah.
Okay, thank you, David. Anyone else? Oh, we have another minute, so I'll ask another one.
Cool.
So way back at the beginning when you're showing your double beta decay spectrum, could you go through again how you discriminate between the 2 neutrino section and the 0 neutrino section?
Yeah, that's a good question. So in this plot, it looks really easy if you're in this case, right? You can say, well, these ones are 2 neutrino and that one is no neutrino. But in this scenario, it looks much harder. So the goal for us in Nexo is first to measure energy very, very well. And by measuring energy very, very well, I mean with small fluctuations, which means that this peak, rather than being broad, it will be narrow. And the narrower the peak, the better separation you'll get from your 2 neutrino double beta decays and your 0 neutrino double beta decays. But it's not the only parameter that we have. I have it in my backup slides here. Yeah, we have many parameters. I didn't get into any of the Nexo analysis stuff, but Nexo is reconstructing the 3D position of the events. Like I said, with the TPC does that automatically. So you get a lot of power just from knowing where your signal is occurring. This allows you to do things like discriminating against background-like events just from the distance from the detector surface. Like, because the TPC is so homogeneous, we can, the signal is distributed like the xenon, which is like a cylinder, but the background is distributed like the walls. So it's all coming in from the outside to first order. And we're getting rid of most of it just by looking away from the walls. So this standoff cut is pretty good. And then topology is like this, is a bit more detailed, but what we do is we combine all of our analysis variables together in a big multi-parameter fit, which is really powerful because it allows us to simultaneously fit the signal in the background together and get the best estimate of what the excess is. And it's hard to explain in few details because a 3-dimensional fit does not look good on a slide, but this is kind of a nice shot of what that looks like when we have our signal that we expect for this set of simulations, where after some of these projections, you can see even with these 2 neutrino backgrounds coming in from over here, we still have a nice little bump that we can look at. So that's one of the really powerful features of the TPC is simultaneous background and signal like event constraints. Yeah.
Okay. Thank you, David. A very nice talk.
Great. Thanks for listening. And if people are interested in some of the work here, it was just written up recently. And if you want to get in touch, this is my contact info on the screen here.
Okay. All right. Let's thank